Ever since the first humans lifted their eyes at night, the glow of a sky dotted with thousands of stars has sparked questions that still echo today. What lies beyond our horizon? How far can we go? Curiosity, paired with technological progress, slowly pushed us out of Earth's cradle. And yet we, with our fragile bodies, barely reached the moon, 250,000 kilometers away, and even that brushed against the very limit of what flesh and blood can survive. But the machines we built, incapable of fear or fatigue, have crossed distances none of us could ever endure. These silent travelers brought back clues about the universe waiting out there. And among them, two sisters stand out above all the rest: the Voyager 1 and Voyager 2 probes, the most distant human-made objects ever created. Nearly 50 years after they left, they are still out there, still moving, still drifting farther from home with every second that passes. How far has the fastest of the two really gotten? And what does that distance actually mean? That's what we're going to uncover in today's video.
We have ignition and we have liftoff.
Voyager 2 launched first on August 20th, 1977, rising off the pad at Cape Canaveral atop a Titan Centaur rocket. Its plan was to visit Saturn, Uranus, and Neptune, but the gravitational dance of the solar system handed it an irresistible prologue, a rendezvous with Jupiter. That stop wasn't in the original script, yet it yielded an extraordinary harvest. As it passed the largest planet in the solar system, the probe imaged the moons Ganymede and Europa in enough detail for scientists to infer the existence of subsurface oceans hidden beneath their frozen crusts. Liquid water, kept warm in the dark, far from the sun. A possibility that, to this day, fuels the search for potentially habitable environments beyond Earth. Next, at Saturn, Voyager 2 measured the planet's temperature and magnetic field, studied the structure of its rings, and identified new satellites, expanding the catalogue of worlds orbiting the Lord of the Rings. The journey continued, and with it came more firsts. On January 24th, 1986, Voyager 2 performed the only flyby of Uranus ever conducted by any spacecraft, returning the first close images and data on the planet. Its dark rings, its strangely tilted magnetic field, and its moons. Uranus, a world tipped almost completely onto its side, rolling around the sun like a marble instead of spinning like a top. 3 years later, on August 25th, 1989, it repeated the feat at Neptune, the most distant planetary encounter ever attempted. There it found the fastest winds in the solar system tearing across the bluest of all the planets, and it confirmed that both Uranus and Neptune wear dark rings made of dust and frozen rock. It even caught Neptune's moon Triton venting icy plumes into space, geysers, on one of the coldest worlds we had ever seen. Neptune's gravity, however, bent the probe's fate beyond what was planned, flinging it for good out of the ecliptic, the flat plane along which most bodies in the solar system orbit. That meant it could no longer approach any other major target in our cosmic neighborhood. But on the other hand, a new chapter opened, the investigation of the environment between the stars. That's how Voyager 2's mission took on a pioneering role in nearby interstellar space. The probe began observing the plasma that drifts between the stars, detecting cosmic winds, measuring the true extent of the heliosphere, that vast bubble sustained by the solar wind, and refining our measurements of stellar distances from its new vantage point. And on November 5th, 2018, it did something only one other object had ever done before it. It crossed the outer edge of the heliosphere and entered interstellar space, sending home the first direct measurements of the density and temperature of the plasma between the stars. Today, Voyager 2 sits about 143 astronomical units from the Sun, just over 21 billion kilometers from Earth, widening the gap at roughly 15 kilometers every second. Impressive numbers, and yet humble on the cosmic scale. It's estimated to take about 42,000 years before it passes near Ross 248, a small red dwarf a mere 10 light-years away in galactic terms, and around 300,000 years in the future, it should pass within about 4 light-years of Sirius, the brightest star in our night sky, which today lies roughly 8.5 light-years from Earth, still a vast distance, but the closest that trajectory will ever bring it to that famous star. It's curious to think that a human artifact can travel so far and still remain completely invisible. The truth is, we simply can't directly observe such a small object at those distances. It disappears into the darkness between the stars. And that's exactly where the more famous of the two sisters comes in. Voyager 1 launched just a few days later, on September 5th, 1977. Yes, we have ignition. We have a liftoff. With the main task of exploring Jupiter and Saturn, early on its gaze revealed features we now consider classics. The detailed swirling storms in Jupiter's atmosphere, new satellites circling the giant, and, surprisingly, a subtle system of thin, dark rings around the planet, something no one had expected to find there. But the masterstroke came with a small moon called Io. The data showed intense volcanic activity, towering plumes of material erupting hundreds of kilometers up into space. It was the first proof of active volcanism anywhere beyond Earth, and it made Io the most geologically violent world we knew of, squeezed and heated by Jupiter's enormous gravity. A powerful reminder that a world which seems dead from a distance can hide dramatic, restless processes deep inside. When Voyager 1 was first conceived, expectations called for a short mission, about 5 years long, collect data from the gas giants, and then vanish quietly into the vastness. But the unlikely happened. It stayed alive far, far beyond that deadline. It crossed the Kuiper Belt, that wide band of icy objects beyond Neptune, born from the leftover rubble of the solar system's formation, and simply kept going. And in 2012, it became the first spacecraft in history to cross the heliopause, the limit where the solar wind is finally halted by the interstellar medium, and pass into the space between the stars. Today, Voyager 1 lies roughly 172 astronomical units from the Sun, about 25.5 billion kilometers from Earth, and it still holds the title of the most distant human-made object from home. In fact, late in 2026, it will reach a milestone nothing we have ever built has touched, a full light day from Earth. From that point on, a single radio command will take an entire day just to arrive, and then a second full day for the spacecraft's answer to make its way back. We will be whispering to it across a gap so wide that even light, the fastest thing in the universe, needs 24 hours to cross it. But distance isn't the same as being outside the solar system. To truly escape the Sun's domain, Voyager 1 still has to cross an even more remote frontier, the Oort cloud. Picture a spherical cocoon populated by countless frozen comets, wrapping around everything, extending out to about 50,000 astronomical units from the Sun, somewhere around 7.5 trillion kilometers. Only after passing through that region could we honestly say the probe has definitively left the solar system. And that will be a very long, slow drama. Voyager 1 will still take tens of thousands of years just to reach that diffuse frontier, and tens of thousands more to cross it. And only then will it head out into interstellar space without ever looking back. After that, its route wasn't planned to meet any specific destination. It is simply a consequence of the initial push and the gravitational tides that shaped its path. One of the closest stellar encounters its trajectory promises, about 40,000 years from now, will be with the star Gliese 445, a faint red dwarf roughly 17 light-years away, and even then it will pass no closer than around 1.5 light-years from it. Nothing cinematic, just a quiet pass at an interstellar distance still enormous, like a balloon carried by the wind that brushes a treetop and moves on. It's beautiful and melancholic at the same time, a reminder that our messengers are persistent, even when no one can hear them anymore, and that the silence is closer than we think, because slowly, year by year, the power is fading. The radioisotope thermoelectric generators, the Voyager's nuclear hearts, have been cooling for almost 50 years, and every single year they produce a little less energy. So mission engineers have been forced to make painful choices, switching off one instrument at a time to keep the most important ones alive just a little longer, like turning off the lights in a house room by room to keep one last bulb burning. As of now, in 2026, each probe still has only a couple of working instruments left, and that faint trickle of data may continue into the 2030s, but not forever. When the silence finally arrives, the signals will stop reaching us, and the probes will continue, mute, forever. Voyager 1, in fact, shut down its cameras long ago to save power, and if for a moment we could switch them back on right now, we wouldn't see a spectacular firmament. The sun would appear only about as bright as a handful of full moons in our night sky, and the rest would be a flat backdrop of darkness with almost no contrast. To see anything truly remarkable out there, we'd have to fast forward thousands of years, by which time the probe's electronics will already have died. If the instruments will fall silent, the message remains. Bolted to both Voyagers travels a copper record plated with gold, a disc carrying the sounds and images of Earth. It holds 116 images and a wave of sound, chosen to describe our entire world to a stranger. Portraits of emblematic places such as the Great Wall of China, the Taj Mahal, the Sydney Opera House, and the Golden Gate Bridge. Recordings of animals and nature, music from across our cultures, the sound of a human heartbeat, and spoken greetings in 55 different languages. It's a bottled hello, cast into the cosmic ocean, a gesture of hope in case some other intelligence stumbles upon it in the distant future, and from those simple clues realizes that we were here once, curious, noisy, and eager for company. Looking at the whole, the Voyagers stand as symbols of an era when we chose to explore with what we had best: ingenuity, patience, and scientific rigor. They revealed entire worlds, corrected our hunches, and opened up brand new questions about hidden oceans, volcanism beyond Earth, tilted magnetic fields, and the true extent of our own solar bubble. Voyager 2, now more than 21 billion kilometers away, advances in silence towards stellar neighborhoods that will only be crossed on timescales far beyond our grasp. And Voyager 1, even farther out, drifts on beyond the edge of the heliosphere, reminding us that leaving the solar system is much more than simply passing Neptune's orbit. It means overcoming a gravitational architecture that stretches for trillions of kilometers. It's natural to ask, if we already know they won't reach anywhere in the everyday sense of the word, why celebrate them at all? Because the value of these missions isn't in planting flags, but in widening the map of what is knowable. They turned suppositions into measurements, gave faces to distant points of light, and taught us to compare storms, craters, rings, and auroras with data in hand. They showed us that the universe isn't a static void, but a living tangle of flows, solar wind, energetic particles, magnetic fields, and shock waves that shape invisible boundaries like the heliopause. In every bit of information they transmitted, there's a quiet reminder: the cosmos may seem indifferent, but it answers when we know how to ask. Of course, there will be a last packet of data, a final faint beep crossing the dark toward our antennas. After that, only the trajectory remains. The Voyagers will wander for ages beyond our memory, crossing planes and gravitational currents, invisible to our telescopes and undetectable to the eye. And yet, their persistent presence will carry something of ours. The idea that we were able to send a trace of rational thought beyond our own atmosphere, complete with instructions, greetings, and our enduring curiosity. Even in silence, they'll keep telling the same story, just in another way, like technological fossils of a species that wanted to understand its place. If you've made it this far, it's because this story speaks to you too. Think of it: 42,000 years to reach Ross 248, 300,000 years for a distant pass by Sirius, tens of thousands of years just to clear the Oort cloud. All of that can feel overwhelming, but it isn't discouraging. It's liberating. It shows that we don't need to reach the end in order to start learning. Each leg, from Jupiter to Neptune, from the Kuiper Belt to the heliopause, has already changed how we see our own cosmic backyard. And in the end, that's what matters. Expanding the horizon of what we know, one flyby at a time, one radio beam at a time, one golden record at a time. The two sisters we launched in 1977 weren't just scientific missions. They were acts of imagination. Soon their instruments will fall quiet, and the signals will stop pinging on our charts. Even so, they'll remain the ultimate travelers. Not because they'll reach a triumphant destination, but because they keep moving. And perhaps that's the truest portrait of who we are. If this journey inspired you, you already know the next step. Leave a like, subscribe, and share. It helps a lot, and it costs nothing. Thanks for watching, and see you in the next video.